Hi everyone, we're Team Urban Microclimate Prediction VIP-SMUR-Kriging. So our team members include me, Benjamin Shi, Taeyang Som, Krish Kuptat, Danasan Chanawa, Yupeng Tang, and Zhou Jia. So today we're excited to present a novel approach to urban microclimate prediction, focusing specifically on the urban canopy layer. And our model, the UMP model, integrates both climate parameters, including air temperature, relative humidity, and dew point, and detailed urban features. So to capture the complexity of these interactions, we use a hybrid deep learning architecture that combines LSTM, transformer, and Kriging components. The ultimate goal of our work is to develop an urban microclimate prediction model that closely reflects real urban environments, improving both accuracy and applicability in real-world settings. So to improve the accuracy of our microclimate model, our team gathers environmental and spatial data that reflect real-world conditions. Let's begin with the first one, geospatial data. So now I'll explain our 2D spatial data. The goal here was to use spatial vector relationship to help interpolate data across the Georgia Tech campus. Basically, we look at how each location on campus relates to key features around it. In the end, we generated a CSV file that records these 12 distances for each point on the grid. This gave us a spatial profile of every location, which we can fit into our model. Next, now moving on to our building elevation data. The objective here was to build on the 2D spatial approach by adding a vertical or elevation-based component. In other words, we wanted to account not just for where things are, but also how tall they are. So this 3D layer helps add more depth to our model by incorporating vertical information like building heights. Next is our building area analysis. The objective here was to understand how building density and footprint relate to microclimate conditions and use their relationship to help predict data more accurately. With the data, we can tell how buildup of the campus can influence things like heat retention and airflow. Next, let's talk about surface materials, which have a strong impact on surface temperature and in turn the local microclimate. By inputting a bounding box defined by maximum and minimum latitude and longitude, the Python script processes the corresponding map tiles and generates an Excel file that maps each coordinate to its surface material type. To maintain accuracy, any coordinates without identifiable color data are excluded from the final outputs. Also, shadow play a role in shaping microclimate. While each shadow may seem minor, the combined effect across all buildings is significant. To assess the effect, we calculate the average shadow coverage, or conversely, average sunlight exposure, as the two are complementary. Finally, a CSV file is generated, containing list features for each coordinate, which is then used as input for the model. Lastly, sun angle is also a crucial parameter in microclimate modeling. Our goal is to use sun angle as a direct input, replacing time series data. This will improve the generalizability of the model, enabling it to accurately predict microclimate conditions across different regions. All the elements mentioned above are the input parameters we've collected for training the machine learning model. Our goal is to leverage geospatial data, surface material classification, shadow patterns, and sun angle information to enhance the accuracy and reliability of our microclimate prediction. By incorporating these environmental and spatial variables, we aim to create a more robust model that better reflects real settings.
So now let's talk about the model development part. I used to use the TFT model and LSTM model separately for this project, but eventually I want to integrate them together to see the results. So I use the temporal fusion transformer with LSTM attention encoder model, and the key components include GRN, VSN, and LSTM with attention encoder and temp to vec and GRN-based encoder. And for the feature engineering selection, I just make some progress compared to before. Now I use core features like relative humidity, dew point, muse, altitude, delta temperature, which reflects the temperature change over time. And to account for time of day effects, we extracted sine R and cosine R as a time feature. And all the features were normalized using min-max scaling to ensure numerical stability during training. And for our training progress, we follow a standard supervised learning workflow. We train the model using the mean squared error loss and the Adam optimizer with weight decay to prevent overfitting. And also to improve the training efficiency, we also use early stopping based on validation loss. And this pipeline ensures efficient convergence while safeguarding against overfitting. We also decided to utilize a neighboring weather station in Atlanta to train the time series aspect. So we utilize the Selenium web scrapping library, and then we were able to retrieve the data frames from the Atlanta International Airport, and we can use this for testing data. Also, we can see the model was trained using the 14 weather stations data in Georgia Tech campus, and we use Atlanta International Airport data for testing. So I just make some things to evaluate and predict the data. Firstly, I created two functions, predict and plot full sequence. They can just compare the predicted data against the actual observations for selected batches. And for quantitative evaluation, I use the RMSE, MAPE, and R-squared to measure accuracy and consistency. And I also conduct residual analysis by plotting error distributions. Actually, during the testing part, I just found some problems. I just say the results were very bad. So after investigation, I discovered that the training data contained extreme outliers in temperature values. It can even reach to 174 Celsius degree. That is very ridiculous. As a result, the normal temperature values in the test set were transformed into very small values during normalization, cause the model to predict in an unusually narrow range. So I filter the training data to a realistic temperature range, and then I train the data and test the data again. And after I fix the problem, I can see the residual distribution become better, and the results showed a slight improvement compared to before. Especially, we can see the residual distribution graph. I just think the metrics of it is very good, but we can see this graph, the result is slightly better than before, but I still don't think it needs some improvement. And actually, for this kind of result, I just think it's because the model still needs some improvements, and maybe there are still some minor problems with the data set. Actually, I hadn't get the data set, I mean the new data set until last night, so I did not have enough time to just make this model better, but I think I will continue to make this better during the summer.
Sounds good. Yeah. I'm not gonna name any names.
Okay, for the result, the model help us to forecast the temperature on a specific time. As you can see, we have different temperature in different weather station around the campus. And
Can you go, is this for 1 hour now? Is this for 1 p.m.? Like a particular day?
It's for a specific time.
Okay, perfect.
yeah,
Awesome.
And then we can use this to like forecast temperature on an average day and also for the specific time that we want to. And moreover, we can like see the correlation between our temperature with the shadow patterns on on our campus to see the correlation between shadow pattern and microclimate factor parameters. Okay, to discuss, I think we can say that our models can enhance the previous method that they use CFD combined with machine learning. And for the future developments, next semester, I think the model should be deployed for practical implications such as we should improve the model to do like a real-time simulation, and we should also explore the high resolution spatial data and temporal data that could be improved, like hyperlocal forecasting. And we don't want to do just only forecast temperature or microclimate parameter. We want to do like simulate urban climate scenario under the different urban context. And we would like to like develop a model framework for deployment across multiple urban areas.
Yep.
And